The results of scientific discoveries are seldom expressed as absolute truths. Absolute truths may be the result of a purely theoretical research which proves a statement, that is a theorem, in a given mathematical setting. In practice, as we observed in earlier lectures, research is an iterative process through which we validate and refine the research results until they reach an acceptable degree of support from experiments. At each stage of this iterative process, research results are an approximation of the real results. In this lecture, we discuss how approximation can be assessed and controlled in the research process. We can frame this problem in a logical setting through the notions of soundness and completeness. When a researcher studies an unknown phenomenon, he or she comes out with a hypothesis which constitute a theory that tries to explain the phenomenon. The theory is sound if all the potential predictions made by the theory are actually observable for the real phenomenon. As the picture shows, a sound theory only allows truths to be deduced, but not necessarily all truths. A theory is complete if it can predict all actually observable manifestations. As the picture shows, a complete theory allows all truths to be deduced, but also, possibly, non-true things. Ideally, the theory should be both sound and complete. The deducible truths from a theory that are not real truths are called false positives. The real truths that are not deducible from a theory are called false negatives. Of course, deducible truths that are real truths are true positives. For example, let us go back to the simple culinary theory we defined in an earlier lecture: all Italians like pasta. The theory is complete since it can predict all Italians who like pasta, but it is obviously unsound. For example, it can be applied to a newborn Italian to deduce that the infant likes pasta. In this example, infants constitute false positives. A refinement of the theory, like all Italians more than 18 years old like pasta, is also unsound, since some existing adult Italians, who are also false positives, may dislike pasta. Let us consider other kinds of research, different from the examples we have discussed so far, which we are all trying to explain real-world phenomena. Suppose that the objective of our research is to solve a novel problem or to find a better solution to an existing problem for which a solution already exists. Typically, in informatics, the focus may be on the invention of a new, clever algorithm for a new problem, or a new algorithm that improves efficiency of known algorithms in terms of computation time or consumed storage. The concepts of soundness and completeness equally apply to problem solutions and algorithms in particular. A sound algorithm never includes a wrong answer, but it might miss a few right answers. A complete algorithm never misses a right answer. It provides the complete set of right answers, but it might include a few wrong answers. A sound algorithm is conservative, pessimistic. Its dogma is to remain on safe grounds to get assurance on its results. On the opposite, a complete algorithm is liberal and optimistic. It is open to more results than may turn out to be invalid in an attempt to include all results. This can be described by this figure. A false negative is a right answer that is not recognized as such by the algorithm. Likewise, a false positive is an answer provided by an algorithm that turns out to be wrong. An exact solution is both sound and complete. However, in many cases it may be impossible or impractical to find an exact solution. We need to accept, and we may be perfectly happy with, approximate solutions. Certain algorithms are neither complete nor sound, and thus exhibit both false positives and false negatives. The number of false positives and false negatives is an indication of the inaccuracy of an algorithm. Approximate algorithms are very common in informatics. A very important reason is that there are many problems that are undecidable. An undecidable problem is a decision problem for which it is impossible to construct an algorithm that always leads to a correct yes-no answer. Undecidable problems are ubiquitous. In particular, most problems concerning program analysis are undecidable. Program analysis refers to analyzing computer programs to verify certain properties that assure absence of bugs in the program or to exclude certain erroneous conditions. A very simple property may be: every statement in the program is executable. That is, it is reachable in some computation. A statement that is never executed is useless. It constitutes dead code. Although well-written programs should not contain dead code, per se, this does not indicate an error in the algorithm. However, it is very often the symptom that there is an error in the program. An algorithm that produces the list of all unreachable statements would be quite useful in program debugging. Unfortunately, this problem is undecidable, and an exact algorithm does not exist. Program analysis research has analyzed this program and produced approximate solutions. A sound solution produces a list of statements that are guaranteed to be unreachable, although there can be more. A complete solution would produce a list of statements that includes all unreachable statements, although they might instead be reachable. Notice that an algorithm that always produces an empty set of statements would be sound, while an algorithm that always produces all statements would be complete. However, these two cases, the number of false negatives and false positives respectively, would be unacceptable. How can we reason about the adequacy of an approximate research result? Two notions are commonly used for this purpose: precision and recall. Precision is defined as the ratio between the number of true positives and the number of true positives plus false positives. In the case of an approximate algorithm, it is the fraction of correct answers among the computed answers. Ideally, it should be 1. Completeness is instead defined as the ratio between the number of true positives and the number of true positives plus false negatives. In the case of an approximate algorithm, it is the fraction of the computed answers over the total number of correct answers.